So in my previous class, I have shown you the questions in the assignment in work for energy, numbering from 31 to 60. Earlier, I have already discussed the solutions of the questions in the assignment in work for energy, numbering from 1 to 30. In the previous class, I have shown you the questions numbering from 31 to 60, and I have even shown you the answers for those questions. Next, I am going to discuss the solutions of the questions numbering from 31 to 60 in the assignment in work for energy. In case you are not having any doubts in the first 10 or 12 questions in this assignment, from 31 to 42, you can skip this class and can go to the next class directly. Come on, look at the question number 31 on the screen. So an elevator is designed to lift a load of 1000 kg through 6 floors of a building, averaging 3.5 meter per floor in 6 seconds. The power output of the engine of the elevator, neglecting other losses, is. So here the total vertical height. So the total vertical height to which the load is raised in 6 seconds is equal to 6 times the height of each floor. The height of each floor is given to 3.5 meters. So total vertical height lifted is 6 into 3.5 meters. So the power output of the engine of the elevator is equal to work done by time. Work done again at the gravitational force lifting through a vertical height h, which uniform speed is equal to mgh. So now m is equal to 1000 kg, g is 10 meter per second square, h equal to 6 into 3.5 meters, time t is 6 seconds. So you get 35 into 10 cube watt or 35 kilowatt. That's the answer. So for question number 31, first option is answer. So look at the question number 32. From waterfall, water is pouring down at the rate of 100 kg per second on the blades of the turbine. The height of the fall is 100 meters. The power delivered to the turbine in kilowatts is also similar to the earlier problem. The power delivered is equal to mgh by t. So m by t gives you the time rate at which the mass of the water is falling per second. So work done by the gravitational force when the body falls through a vertical height h will be mgh. So divided by time interval gives you the power delivered to the turbine by the falling water. So m by t is 100 kg per second. G is 10 meter per second square. H equal to 100 meters. So that will be 100 into 10 cube watt, or 100 kilowatt is the answer. So we have discussed the question number 32. First option is the answer. See the question number 33. A horizontal force of 70 Newton is applied on a block of weight 100 Newton, which is initially at rest on a rough horizontal floor. Nu k equal to point. What is the average power used for first 4 seconds? So to find the average power for first 4 seconds, you have to calculate the work done for first 4 seconds. And to calculate the work done for first 4 seconds, you have to find the displacement covered in the first 4 seconds. And to find displacement covered in the first 4 seconds, you have to first calculate the acceleration of the block. And to find the acceleration of the block, you have to apply Newton's second law. So let us consider the forces which act on the block here. The first external force which acts on the block is its weight mg, which is the gravitational force of the block by the earth. Then let capital F denote the horizontal force applied on the block with external agent, whose magnitude is given as 70 newtons. The force of kinetic friction. The force of kinetic friction on the block by the surface of floor acts opposite to the direction of the motion of the block, that is opposite to the horizontal force applied. Let Fk denote the magnitude of kinetic friction of the block. Here N is a magnitude of normal reaction force on the block by surface of floor, which acts vertically about perpendicular to surface of floor and directed away from surface of floor. I choose the horizontal direction. That is the direction of the horizontal force applied as positive direction of x-axis and vertical upward direction of the y-axis. So y component of resultant force on the block is denoted by phi, that you can write n minus mg. But here the block has no acceleration in the vertical direction. So y component of acceleration is 0, y component resultant force is 0. So magnitude of the normal reaction of the block is same as the weight mg of the block. So magnitude of kinetic friction on the block during the motion is equal to product of coefficient of kinetic friction to magnitude of normal reaction. Magnitude of the normal reaction is equal to mg. So nu k is given to 0.28 mg of the block is given to 100 newtons. So magnitude of kinetic friction of the block will be 20 newton. As the block has no acceleration parallel to y-axis, the resultant force of the block will be equal to Fx, means resultant of forces in the x direction. Here capital F is the magnitude of the horizontal force applied on the block, which acts along positive x-axis in the direction of the motion of the block. Fk represents magnitude of kinetic friction of the block, which acts opposite to the direction of the motion of the block. So magnitude of the resultant force of the block along x-axis equal F minus Fk. According to Newton's second law, magnitude of the resultant force of the block will be equal to product of its mass and acceleration. Now here the weight mg of the block is given to be 100 newton. And the acceleration due to gravity is given to be 10 meters per second square. So you get mass of the block equal to 10 kg. So you can substitute capital horizontal force applied to the block is given to be 70 newton here. So on the left hand side you can write capital F equal to 70 newton, Fk equal to 20 newton. The mass of the block is 10 kg. So you get magnitude of the acceleration of the block as 5 meters per second square. So if the body starts from rest and moves with constant acceleration, then displacement covered in time t is given by s equal half at square. So the acceleration is equal to 5 meters per second square. To find the displacement covered in first 4 seconds, put t equal to 4 seconds. So displacement covered in the first 4 seconds is 40 meters. So work done by the agent pulling agent in first 4 seconds is equal to product of magnitude of force applied by the agent into magnitude of displacement. If a constant force acts in the direction of the displacement, Then work done with a constant force is given by F into S. That is product of magnitude of force and magnitude of the displacement. Magnitude of the force applied is 70 newtons. Magnitude of the displacement is 40 meters. So average power delivered by the agent for the given time interval is equal to work done by the agent divided by time interval. Work done by the agent is 70 into 40 joules by 4 seconds. So 700 watt is the answer. So if you want to copy down the solution of the problem, you can take a pause and copy down the solution of the problem. So for question number 33, which I just now discussed, the first option is answer. Next, look at the question number 34. A horizontal force applied on a block of weight 100 Newton, which is initially at rest on a rough horizontal floor. The force is just sufficient to start the block moving, and if the same force continues to act even after the motion begins, then what is the instantaneous power at the end of 4th second? So to find the instantaneous power at the end of 4 seconds, you have to find the magnitude of force applied on the block by the external agent, and you have to also calculate the magnitude of the instantaneous velocity at the end of 4 seconds. To find the instantaneous velocity at the end of 4 seconds, you have to find the acceleration of the block. And to find the acceleration of the block, we have to apply Newton's second law. So let us consider the forces acting on the block here. The weight mg of the block acts vertically downwards, which is the gravitational force of the block by the earth. Then the normal reaction force on the block by the surface of floor acts perpendicular to surface of floor and directed away from surface of floor. That is the acts vertical upwards. Let capital F denote the magnitude of the horizontal force applied on the block by the external agent, which acts suppose towards right. I choose the horizontal direction, that is the direction of the force applied on the block as x-axis, and vertically upward direction as positive y-axis. The frictional force on the block by surface of floor opposes the motion of the block relative to floor. So the force of friction on the block by surface of floor acts opposite to the horizontal force applied. So Fy, that is y component of resultant force of block, we can write n minus mg. That will be 0. So magnitude normal reaction of the block is same as the weight mg of the block. Here the horizontal force applied on the block is just sufficient to start the block moving. That means the horizontal force applied on the block magnitude of the horizontal force applied on the block can be taken to be equal to the magnitude of the limiting force of friction. Because if the block is initially at rest, the block starts moving only when the magnitude of the horizontal force applied on the block just exceeds the magnitude of limiting friction. So magnitude of the horizontal force applied on the block can be taken to be equal to the magnitude of the limiting friction, or maximum value of force of static friction, which is equal to nu s into n or nu s into mg. Here nu s is given to 0.6, weight mg of the block is given to 100 newtons. So magnitude of the horizontal force applied on the block is 60 newtons. So y component resultant force is 0. Therefore resultant force of the block is equal to x component resultant force, which is denoted by Fx. Here capital F is the magnitude of the horizontal force applied on the block by the external agent, which acts along positive x-axis in the direction of the motion of the block. F small, after the block starts moving, frictional force on the block will be equal to the kinetic friction. Magnitude of this kinetic friction is denoted by Fk, which acts opposite to the direction of the motion of the block. From Newton's second law, resultant for the block can be equated to product of its mass and acceleration. So the weight mg of the block is given to 100 newtons, and g is equal to 10 meter per second square. So you get mass of the block as 10 kg. So you can substitute here F equal to nu s into mg. If k is the kinetic friction, magnitude of kinetic friction is equal to nu k into Narwhal reaction. Magnitude of Narwhal reaction equal to mg here. If you divide the equation with the mass m, we get magnitude of the acceleration of the block is equal to given by nu s minus nu k into g. Nu s equal to 0.6, nu k equal to 0.4. G is 10 meter per second square. So magnitude of the acceleration of the block will be 2 meter per second square. So the block starts from rest and moves with constant acceleration. Then magnitude of the velocity after time t is given by v equal to u plus at. Here initial velocity u is 0, so you can write v equal to a into t. A equal to 2 meter per second square. To find instantaneous velocity after 4 seconds, you have to substitute a equal to 4 seconds. So instantaneous velocity at the end of 4 seconds is equal to 8 meter per second. So instantaneous power at the end of 4 seconds equal to product of the magnitude of force applied instantaneous velocity at the end of 4 seconds. The general case we write f bar dot v bar or f cos theta. Here the angle between the direction of the force and direction of the velocity is 0 degrees. So theta is 0 degrees. F cos 0 degrees or f into v. So magnitude of the force applied by the agent on the body is 60 newtons. Magnitude of the instant of velocity is 8 meter per second. So you get the answer as 480 watt. So if you want to copy down the solution of this problem, you can take a pause and copy down the solution of the problem. So for question number 34, second option is answer. Next you see the question number 35. Block of mass 2 kg. Pull it up on a smooth incline of angle 30 degrees with the horizontal. Block moves with acceleration of 1 meter per second square. What is the average power delivered during the 4 seconds after the motion starts? So here we have to first calculate the magnitude of the force applied on the block by the pulling agent along the inclined surface. So let us consider the forces acting on the block. Let capital F denote the magnitude of force applied on the block by the external agent, which acts in the direction of the motion of the block. The weight mg of the block acts vertically downwards. The Narwhal reaction force on the block by the smooth inclined plane acts perpendicular to the inclined surface and directed away from the inclined surface. Can resolve this weight mg of the block into rectangular components parallel to the inclined surface and perpendicular to the inclined surface. The theta denote the angle of inclination of the inclined plane to the horizontal. So the component mg cos theta acts perpendicular to the inclined surface. The component mg sin theta acts parallel to the inclined surface down the inclined plane. I choose the direction parallel to the inclined surface up along the inclined surface as x-axis. And direction perpendicular to the inclined surface as y-axis. There is no friction here. The inclined plane is smooth and frictionless. The block has no acceleration parallel to y-axis, so y component of resultant force of the block must be 0, or Fy must be 0. So resultant force on the block will be equal to Fx. That means x component resultant force. Here capital F is the magnitude of the force applied on the block by the pulling agent, by the external agent which acts in the direction of the motion along positive direction of x-axis. The component mg sin theta acts down the inclined plane opposite to the direction of the motion. So magnitude of the resultant force in the direction of the motion will be capital F minus mg sin theta. From Newton's second law, this can be equated to product of its mass and magnitude of acceleration. So magnitude of force applied on the block by the external agent, we can write it as m into g sin theta plus a. Come on, substitute all the given numericals. The mass of the block is given to be 2 kg. G is given to 10 meter per second square. The angle of inclination of the inclined plane to the horizontal is 30 degrees. The acceleration of the block is 1 meter per second square. This you can simplify it further. So you get F equal to 12 newtons. So work done by the agent in 4 seconds. Equal to product of the magnitude of force applied by the agent displacement in 4 seconds. The body starts from rest and moves with constant acceleration. Then magnitude of displacement covered in time t is given by equal to half at square. To find the magnitude of displacement covered in first 4 seconds, you have to take t equal to 4 seconds. The acceleration is given to be 1 meter per second square. That comes out to be 8 meters. So work done by the agent, I mean pulling agent, in the first 4 seconds. You got to product of the magnitude of the force applied by the agent on the block multiplied by the magnitude of the displacement of the block. Magnitude of the force applied by the agent is 12 newtons, magnitude of the displacement is 8 meters. So average power delivered by the agent is equal to work done by the agent divided by time interval. The time interval is 4 seconds. That will be 24 watts. So if you want to copy down the solution of the problem, you can take a pause and copy down the solution of the problem. So here, 35th question, you get the second option as answer. Next, look at the question number 36. Person wanted to use his bathtub to generate electric power to run a 60-watt bulb. The tub is located at a height of 10 meters from the ground and it holds 200 liters of water. Installs a water-driven wheel generator on the ground. The rate of water drain from the bathtub to light the bulb is. So you have to find out first mass of the water that is pumped out per second. Now the power to be used by the bulb is 60 watts. That means the power output can be taken as equal to 60 watts here and the efficiency is 60%. That means power output is 60% of actual power. You can write power output 60 by 100 times the actual power. So here power output required is 60 watts. So the actual power to be generated denoted by P subscript A. So the actual power to be generated will be 100 watts. This power is generated by the falling water. Therefore, if m is the mass of water that falls from given height h in time t, then the power delivered by the falling water to the generator is equal to mgh by t. The power to be generated is 100 watts. Let m denote the mass of the water that falls per second in a time interval t equal 1 second. G is 10 meter per second square. H is given to be 10 meters. That means 1 kg of water must be falling per second. So volume of the water that falls is equal to mass of the water by density. The mass of the water that should be made to fall per second is 1 kg. Density of water 10 cube kg per cubic meter. So that is 10 power minus 3 cubic meter or 1 liter. That means 1 liter of water must be falling per second to generate the required power. So if you want to copy the solution of the problem, you can take a pause and copy the solution of the problem. So for question number 36, first option is the answer. Next, see the question number 37. A particle moves in a straight line with a constant acceleration along a smooth horizontal floor under constant force F. The correct statement is, you have to find the relationship between power developed by the force and time t here. The force is constant and acts in the direction of the motion. So three forces act on the particle here, weight mg and normal reaction by the surface, and force applied by the pulling agent or source. There is no friction in the problem. So the resultant force is same as the horizontal force applied on the particle by the external agent. The weight mg of the particle is balanced by the normal reaction force. So the resultant force is same as the force applied on the particle by the agent. And from Newton's second law, that can be written as product of mass and acceleration. So acceleration you can write F by m. So instantaneous velocity after time t given by v equal to at. The particle starts from rest and moves with constant acceleration. So that is F by m into t. So instantaneous power developed in time t is given by F into v. That is F into Ft by m. So equal F square by m into t. So power F is a constant in the given example, and mass of the particle can also be assumed to be constant. So the power developed by the force varies linearly with time. Therefore, first option is the answer for this question. Next, I am going to discuss the next question, 38. See the question number 38. An electric pump on the ground floor of a building takes 10 minutes to fill a tank of volume 30 cubic meter with water. The tank is 60 meters above the ground and the efficiency of the pump is 30%. How much electric power is consumed at the pump in filling the tank? So the efficiency of the pump is 30%. That means the power output denoted by P subscript 0. That is 30% of actual power. That is 30 by 100 times actual power denoted by P subscript A. So the actual power required 100 by 30 times the power output. P subscript O is the power output. So the power output or power delivered is equal to can write mgh by T, where m is the mass of the water that is lifted in time T. Now substitute all the given values here. That mass of the water pumped is equal to volume into density. The volume of the water that is fills the tank is 30 cubic meter. Density of water can be taken as 10 cube kg per cubic meter. So the mass of the water which can fill the tank will be 3 into 10 to the power of 4 kg. And H is given to be 60 meters. And time is 10 minutes, means 10 into 60 seconds. So substitute all these numericals in this equation. So actual power is 100 by 30, that is 10 by 3 into mgh. M is equal to 3 into 10 power 4 kg. Let's take G as 10 meter per second square. And H is equal to 60 meters. The time T is 600 seconds. This you can simplify it further. So 10 power 5 watts or 100 kilowatt. If you want to copy the working, you can take a pause and copy down the working. So for question number 38, first option is the answer. See the question number 39. The velocity of the body is increased by 1 meter per second. Kinetic energy increases by 44%. The original speed of the body in meter per second is. So let V1 denote the original speed and V2 is the new speed. Let K1 denote the original kinetic energy and K2 is the final kinetic energy. So K1 you can write half mv1 square, K2 is equal to half mv2 square. M is the mass of the body which is a constant. So ratio of the final and initial kinetic energies is equal to V2 by V1 whole square. So you can write K2 V2 by V1 is equal to root of K2 by K1. So given that the kinetic energy increases by 44%. So ratio of the new kinetic energy to original kinetic energy will be 100 plus 44 by 100 or 144 by 100. V2 is the new speed. New speed you can write V2 can be written as original speed V1 plus increase in speed. That is 1 meter per second. So you can write V2 equal to V1 plus 1 meter per second on the left hand side here in the numerator. Divided by V1 equal to 12 by 10. Can simplify it further. and complete the calculation. You can copy down this working and complete the calculation yourself. So for question number 39, first option is the answer. Next, look at the question number 40 here. An unloaded car moving with velocity v on a level road can be stopped in a distance f. The passengers add 25% of its weight and braking force remains the same. The stopping distance at velocity v is now. So here we can apply the work energy theorem. We are changing the kinetic energy equal to work done by the external force. The body stopped, final kinetic energy can be taken as 0. The initial kinetic energy you can write half mu square. So assume that the retarding force is constant and same in both the cases. Work done by constant retarding force when the body is stopped in a linear distance f in the horizontal direction. You can write m minus f into s. Therefore, s can be written as, that means the body of mass m moving in a straight line path with initial velocity u is brought to rest by applying a constant retarding force of magnitude f. Then assuming one-dimensional motion, you can write s equal to mu square by 2f. So s2 is the distance in the first case. S1 is the distance in the, S1 is the distance covered in the first case, S2 is the distance in the covered in the second case. That means the body is brought to rest, the distance S1 in the first case. And M2 is the mass in the, total mass in the second case, and M1 is the total mass in the first case. The braking force is same in both the cases, and initial velocity is also same. So S2 by S1 equal to M2 by M1. It is given that the total weight of the passengers increased by 25%. So ratio of the new mass to the original mass, you can write 125 by 100. So S2 will get 1.25 times S1. So if S1 is S, so S2 will be 1.25 into S. So for question number 40, first option is answer. See the question number 41. Block of mass 200 grams slides down an incline of inclination 37 degrees with a uniform speed. The work done by the friction force of the block as the block moves through 50 centimeters down the incline is equal to. So here we can solve the problem by applying the work energy theorem. So when the block is sliding down the fixed inclined plane, the forces which act on the block, let us consider the force acting on the block when it is sliding down the fixed inclined plane. The first axial force which acts on the block is its weight mg, which is the gravitational force of the block with earth. Then second force is the normal reaction force of the block by surface of the inclined plane. Then the force of kinetic friction on the block by the inclined surface acts up along the inclined plane. There are two ways you can solve the problem. One method is by the work energy theorem. The alternate method is you can use the dynamics method. So according to the work energy theorem, the change in the kinetic energy of the block is equal to total work done by all the forces acting on the block. That is work done by the gravitational force of the block. I mean delta K present change in the kinetic of the block is equal to work done by gravitational force of the block plus work done by frictional force of the block plus work done by the normal reaction of the block. The block is sliding down with uniform speed. That means magnetic velocity is constant. The mass of the body is also always assumed to be constant. It is given to 100 grams. Speed is constant, mass of the body is constant. Therefore, kinetic energy remains constant. Therefore, change in the kinetic energy of the block during the motion down the inclined path is 0. Work done with the gravitational force of the block, we have to find out. To find work done by friction. Work done by normal reaction of the block can be taken as 0 because the normal reaction force of the block acts perpendicular to the direction of displaced block. So work done by force of friction of the block. W subscript small f represents work done by friction force of the block. Equal negative of work done by gravitational force of the block. As I discussed in the past, the block falls through a vertical height h. Work done with the gravitational force on the block, you can write mgh. So work done by the gravitational force of the block, when the block falls through a vertical height h is given by mgh, wg equal. So work done by frictional force of the block, you can write minus mgh. So if S is the magnitude of the displacement of the block along the inclined plane, and h is the corresponding vertical height through which the block falls as it slides down the incline, and theta is the angle of inclination of the inclined plane, then you can write sin theta equal to h by s, or h can be written as s into sin theta. So therefore work done by the force of friction of the block can be written as, can substitute here h equal to s into sin theta. So minus mg s into sin theta. Now we can substitute all the given values. Mass m is given 200 grams, means it is 0.2 kg. You are given the value of acceleration due to gravity as 10 meter per second square. So you can substitute g equal to 10 meter per second square. Magnitude of the displacement of the block 50 centimeters, means 0.5 meter or half meter. Sin theta is sin 37 degrees, which you can write 3 by 5. So this you can simplify further. You get work done by the friction for the block minus 0.6 joule. That's the answer. In case you want to copy the solution of the problem, you can take a pause and copy the solution of the problem. So for question number 41, first option is answer. You can also solve this problem by the dynamics method. That means you can calculate the magnetic friction of the block. I am talking about the alternate method for same problem. The resultant for the block down the inclined plane, when it is sliding down the rough inclined plane, you can write mg sin theta minus fk. If you choose the direction of the motion down the inclined plane as a positive x-axis, fk is magnetic kinetic friction in motion. That is equal to mass into acceleration. But here it is moving with constant velocity, therefore acceleration is 0, resultant for the block is 0. So magnetic kinetic friction of the block is equal to mg sin theta. So work done by the force of friction of the block, we denote it by W subscript f. That is equal to fk into s into cos 180 degrees, because force of sliding friction or kinetic friction acts opposite direction of the displacement of the block. Or you can write minus fk into s. In this case, magnetic kinetic friction on the block is same as the magnetic component mg sin theta. So minus mg sin theta into s. So we have arrived at the same result. by the other way. Now we can substitute all the numerical values and simplify it as we have done in the previous method. Look at the question number 42 here. I even drawn the free body diagram on the right side already. Block of mass m is dragged along a fixed oriented surface, coefficient of friction 0.2 at constant velocity of 5 meters per second by applying a force F bar at an angle of 30 degrees above the horizontal. The work done by the force F bar when the body moves 2 meters along surface is 100 joules. And the work done by the friction force of the block is. This problem can also be solved by using work energy theorem. Here the mass of the block can be assumed to be constant and velocity is also given to be constant for the given displacement. So if mass velocity is constant, you can assume kinetic energy to be constant. So as the kinetic energy is a constant, change in the kinetic energy can be taken as 0. According to the work energy theorem, change in the kinetic energy of the block when the block moves 2 meters along the surface is equal to total work done by all the force acting on the block. That is work done by the force F bar plus work done by the force of friction of the block plus work done by the gravitational force plus work done by the normal reaction. Here W subscript N represent work done by the normal reaction force of the block. That will be 0 because the normal reaction force on the block acts perpendicular to the direction of the motion of the block here. W subscript G, the work done by the gravitational force of the block, that is also 0 because the gravitational force acts perpendicular to the direction of displacement. The kinetic of the block is constant, therefore change in kinetic is 0. W subscript capital F represents work done by the constant force F bar applied on the block. W subscript small f represents work done by the force of friction of the block. Therefore, you get work done by the force of friction of the block is equal to minus of Wf. So given that work done by the constant force F bar applied on the block by the external agent is 100 joules. Therefore, work done by force of friction on the block will be minus 100 joules. That's the answer. I will continue the discussion of the remaining questions in my next class.